So we have a merry-go-round that weighs 40 kilograms and a child that sits on the edge of this merry-go-round that weighs 30 kilograms. The merry-go-round is rotating counterclockwise with the speed of 0.8 radians per second. Part A is asking us to find the magnitude and direction of the angular momentum of the merry-go-round and then of the child. So to find the direction, that's easy by using the right-hand rule. All we just do is R cos B, and we get that it's out of the page. Now to find the angular momentum of the merry-go-round, we know that that's equal to the moment of inertia times its angular velocity. A merry-go-round is a solid disk, so we're going to use this equation, 1/2 mr squared, for moment of inertia. So we know that the angular momentum is going to be 40 kilograms times 3 meters squared, and then it's going at 0.8 radians per second. And then when we multiply all of that out, we get 144 kilograms meter squared per second. Now we're going to find the angular momentum of the boy. So we know that this is going to be the cross product of the radius and the momentum vector. So we know that this is going to be r p, or r rho sine of theta. And since the angle between the r vector and the momentum vector is 90, we know that it's going to be r times momentum times sine of 90, which is just 1. So we know that he weighs 30 kilograms, and then the radius is 3 meters. And then we want to translate this to linear velocity, so we do angular velocity times the radius, so that's 0.8 times 3 meters. And we do all of that out, we get that it's 216 kilograms meters squared per second. So part B is asking us to find the angular momentum of the merry-go-round if this boy jumps straight upwards with a velocity of 3 meters per second. So if you want to find this angular momentum right when the boy jumps off, if we think about it, we know that it's just going to be the momentum of the boy and the merry-go-round before he jumps off minus the angular momentum of the boy when he jumps off. So we know that the angular momentum of the boy and the merry-go-round, we found those individually in part A, so we can just add those up here. And then minus this new angular momentum of the boy, which is just r times the momentum times sine of theta. And since he's jumping straight upwards, theta is just 90. So it's going to be 360 minus the radius, which is 3 meters. He weighs 30 kilograms, and then he's with the speed of 3 meters per second, and then that's sine of 90. And then we get that this is 90 kilograms meters squared per second. And we know that this is the angular momentum of the merry-go-round. And if you want to find how fast that is, the angular speed of it, we set this back equal to the moment of inertia times the angular velocity. So we know that it's 90 kilograms meters squared per second, but we just want to find the angular velocity of this merry-go-round. So we do 1/2 mr squared times omega. So we do the 40 kilograms of the merry-go-round times the radius of 3, and then square it, and then we will get this is 90 kilograms meters squared per second, and then when we multiply these out, we get 180, so then that would be 90 over 180, and that would just be equal to 0.5 radians per second. Now part C is similar to part B, but we just want to know what if the boy jumps straight to the right with the velocity of 3 meters per second. So that would look like that. So using the same concept as for part B, we take the angular momentum of the boy plus the merry-go-round and subtract it from the angular momentum of the boy when he jumps off the merry-go-round. So we got the 360 from part A when we added the two individual ones, minus angular momentum again is r times the momentum times sine of the angle. So we know he's 3 meters, this is radius. He weighs 30 kilograms and his speed is 3 meters per second. But then this angle between them is 0, so it's just sine of 0, which is 0. So we have our angular momentum of the merry-go-round being 360 kilograms meters per second at minus 0. So again, like in part B, we just set this new angular momentum equal to the moment of inertia times the angular velocity. So we have 360 is equal to 1/2 the 40 kilograms of the merry-go-round. Since it's a solid disk, we do 1/2 mr squared, and then its radius is 3. And then we have, when we multiply all this out, we get 40 times 9 divided by 2, which is 180. So we have 360 over 180, which is just going to give us 2 radians per second as our angular velocity. Now part D says that we want to keep the angular velocity of the merry-go-round after the boy jumps off to be 0.8 radians per second. So if this is true, we want to find what angle the boy has to jump in order to achieve this. And when we have the speed of 0.8 radians per second, we already know that the angular momentum of the merry-go-round is 144 kilograms meters squared per second, because that's just the moment of inertia times omega, where omega is 0.8, so it's just like part A. So we can set this number equal to this equation that we've been using for part B and C when we take the angular momentum. So we can take this angular momentum of the merry-go-round and the boy and subtract it from the angular momentum of the boy when he's jumping off. So we know that it's 360 minus boy's 30 kilograms, and he jumps with the speed of 3 meters per second, and his radius is still 3 meters. So then we're gonna get, we can do 144 minus 360, which would give us negative 216, is equal to, when we multiply all this out, we get negative 270 sine of theta, and then we divide 270 over, and we get 0.8 is equal to the sine of theta. So if you want to find out what theta is, all we have to do is take the inverse sine of 0.8, and we get 53.1 degrees.